I'm Jamie with Chegg Tutors. Today I want to talk to you about capacitors, and specifically what happens when capacitors in a circuit are connected in parallel. Now let's review what parallel actually means. So as we see in this diagram here, there are n capacitors all connected in what we call parallel. That is, there are branches, and each of those branches has a capacitor on them, rather than each of those branches being all one circuit, one loop, and having each capacitor in series, connected one after another. Now, capacitors in parallel, this is the fundamental thing, behave just like resistors in series. And let me tell you why. So capacitors store up energy. The units of capacitance are charge per voltage. Capacitors store up energy only depending on the geometry of the capacitor. For example, if it's a disc or a plate or a cylinder, something like that. And capacitors store up energy, so we can understand why capacitors in parallel add up in terms of their capacitance. If we store up a certain amount of energy in capacitor 1 here, and we store up a certain amount of energy in capacitor 2 here, then the equivalent amount of energy that we've stored up is just the equivalent energy of what's stored in capacitor 1 and what's stored in capacitor 2. Now, this is different from resistance, where the current is split between different resistors when the resistors are in parallel, so we have to add them differently. The current isn't just slowly decreased as we go from resistor to resistor like it is in series. So capacitors in parallel, if we have a certain capacitance, the unit for capacitance is a farad, which is a coulomb per volt. Capacitors add in series. So if we have a very complex circuit, we want to break this up into simpler circuits. So we can replace this with a circuit that has this. This is the two terminals. It has a capacitor, one capacitor only. Sorry, that's a resistor there. It has one capacitor only, and that capacitor has a capacitance of C1 plus C2 all the way to Cn. So this is C. This capacitor has a capacitance C1 plus C2, C1, all the way to Cn. Now this is not that useful in very simple capacitance problems. You really need to know the actual definition of capacitance and to deal with that. But in more complex circuit problems, you can reduce something as complex as n capacitors in parallel to one simple capacitor and analyze the circuit as if there's just one capacitor. This makes it much easier to deal with complex circuits and reduce them to simple circuits that are only in parallel or only in series. Similarly, if you have capacitors in series, they act like resistors in parallel, and so you can reduce something that has a zillion capacitors, or let's say like 12, to something that has simply 2 capacitors or even 1 capacitor by considering what's in parallel and what's in series. Now, normally in a circuit, you're going to have some things in parallel and some things in series, and you're going to have to deal with that. For example, you might have another capacitor here that's in series with capacitor 2. And then you're going to have to deal with both capacitors in series and parallel. But as a basic way of analyzing circuits, we do want to break this up into capacitors in parallel and a different technique for capacitors in series. That's it for now, and more next time.